somebody, and then the rest of the world goes away. Yeah.
We gotta get this guy out.
Yeah, he's got a bug up his butt, I guess. I don't know what's going on.
All right, we're going to start the meeting. It's time to pay attention. Welcome, everybody. Thank you. Okay, so Mount Diablo Astronomical Society, we are starting the September general meeting. Thank you all for joining. Do we have any new members this evening? Oh, right here. All right, one newbie. Thank you for coming. If you need to use the restrooms, they're through the hallway here. Okay, we're going to have a break after I am our What's Up speaker this evening. So after my speech, we'll have a quick break. So the agenda, starting now, we'll do the announcements, then we'll have my presentation, and then our main speaker is Jeff Adkins. I have Leary in my head, so I didn't forget. But before we do that, Leary has an announcement that he would like to make real quick.
Okay, for those that have Dobsonian telescopes that are motor driven, there's a company called Servacat, and they provide motors for the big Dobsonians. Unfortunately, the company is closing, and the owner is retiring, and they're having difficulty finding somebody else to pick up managing that system. So just be forewarned that if you have a Servacat, yeah, things are going to be a little difficult in the future.
Okay, so not the best news.
Everybody's got to retire.
Okay, just a couple of announcements here. We've got, let's see, our public astronomy night in October coming up after this one. Here we go. Public astronomy night Saturday the 27th, and then the one in October right here on the 11th. There is a schedule change for the October meeting. If you'll see, unfortunately, the Lindsay Wildlife Museum had a schedule conflict, and they weren't really aware of it, but the director helped. She found it and contacted us. So they have a museum-wide event that evening, and they need this room, and they don't have another place for us to host our meeting. So the October general meeting is going to be Zoom only. I will send out an announcement as well, but just make sure you don't show up here unless you want to trick or treat with the 5-year-olds, okay? I'm going to give the what's up this evening, and I am talking about my Yosemite and Barcroft adventures. And so it was my first time for the Mount Diablo Astronomical Society participating in our Yosemite Star Party, and it was a blast. And I think I have finally learned how to use my telescope for visual observations. It's taken years. It's kind of silly to be able to set up for pictures and not know how to do it, but it was pretty challenging for me. But a huge thank you to Renee Gandolfi. I know there was a lot of back and forth and a lot involved in organizing this. I think there were about 20 of us that went up, end of July, early August. We had 2 astronomy nights. This is Bridalveil Falls. This is my first time at Tunnel View and my first time going up to Glacier Point. I'd never been up there. And this is the view. You drive in and it's like, Washburn Point. You're like, oh my gosh, this is heaven. So it was really an amazing trip up above the valley for the first time like that, and really enjoyed Yosemite during the daytime. On one night we hiked to Taft Point, and I literally crawled out there. And it was the stillest day possible, but the tiniest breeze touched me and I panicked that I was going to get blown off the ledge. We also went up Sentinel Dome and hiked around, and you get a 360 view of the valley. It's amazing. This is me with my scope at Glacier Point. And this
Hey, Tara?
Yes.
I'm sorry, this is Rick, but I don't think any of us are seeing your presentation.
Oh, thank you. That would be really sad. Let's try this again. Where'd my Zoom window go now? Thank you, Rick. Okay, can you guys confirm on Zoom? Does that
Yep.
Work. Yep. And you're seeing, let's see, I have to find my presentation again. I apologize. Are you seeing pictures of me on Yosemite at Glacier Point? On Zoom?
Yes.
Thank you guys.
Yes.
All right, appreciate it. Okay, carrying on. I always have to do something technically glitchy. It's my trademark. So this is me on Glacier Point, right there with my telescope, and this is Bridal Falls again, and that was a campground we stayed at. The public astronomy night, we had about 100 guests come and look through the telescopes. It was really rewarding. They asked a lot of great questions. And then around 11:30, they all started trickling out. And then I set up my, small camera system because I use I use a couple of applications to plan pictures ahead of time. And I noticed that from Glacier Point, looking at Half Dome, you can see, let's see if this will play, that the California Nebula and then the Pleiades were going to rise right behind Half Dome starting around midnight, so conveniently after the public astronomy viewing was finished. And so I did, and then after the Pleiades and the California Nebula, the Flaming Star Nebula was going to rise in the tadpoles. So I said, oh, okay, I want to take pictures of that. And so this is my setup. Yes. Is somebody in Zoom saying anything? Okay. It's just, I have a Canon EOS RA, which is astromodified in an 85mm lens. And on top of it, I put my little guide scope. So I was able to take 3-minute exposures. I have a ZWA AM5 mount. And the time lapse that I'm about to show is without guiding. It's just when we look out at the night sky, we see a few stars. We can see the Pleiades, the sky is not black, but it's pretty close. When you take a camera without a tripod, without a mount, you can see better than the eye, but still nowhere near what you can with stacking. So I did a time lapse of the California and the Pleiades rising behind Half Dome, where I used the biggest aperture on my lens, which is f1.2, and at 85mm, the maximum exposure you can take is 6 seconds and a 6400 ISO, so pretty high. And this is what I was able to come up with. So you can see hints of the California Nebula. You can see the Pleiades rising. It's pretty fun. It's okay, right? But it's not breathtaking. And then the next one is the tadpoles and the Flaming Star. You can kind of see the open cluster here. You can kind of see the nebulosity there. Now I've turned on my tracker. You can see it better, and I went till morning. So as I was leaving, the sunrise people were pulling in for the day. Kind of cool, but not, I would say not super compelling. But for me, I like to do what's called the deepscape photography because it personalizes the adventure and it gives perspective and depth and personal meaning to the scene while I was there. So I stacked almost 2 hours of 3-minute exposures on my tracker. You saw, the tracker going up to the stars to create a deepscape image, which means that I didn't change the scale of anything. 85mm is nice because I feel like it's what you can see as your focused looking, it's kind of real to life as pixels on a computer screen can be, in an imagination of what's really out there. And so this is what I came up with. And so this is the dust in Taurus. So the sky is not black. That whole area around the Pleiades and my other time lapse, you can't really appreciate it, but it's all over the place. And this is the Flaming Star Nebula, the tadpoles, and just amazing. If we could see this when we were outside, I don't know if it's sleep, we would all be nocturnal. We'd just be staring up the sky all night. Okay, the next night, again, we had another 100 people. And politely, after everybody left, we had one of the transits of Titan over Saturn.
Bill probably got the same treatment.
Yeah, and Bill, so I know a few of our members have gotten this. So I was just happy to have the shadow and a little bit of the Cassini division. I think I took a 2-minute exposure, like I had best of 20,000 frames. I think I stacked 25% of them. It's crazy. It's not spectacular, but it's mine, and it was a great experience. Okay, and then at the end of the month, we had another adventure. So it was my first time to Barcroft. Barcroft Station is at 12,000 feet, so really high elevation. It's some of the darkest skies we actually have in the United States. Interestingly, while I was up there, I could see the lights from Vegas very easily. So that's definitely encroaching on it. So we came prepared for viewing through, these big Dobsonians that these, astronomers had brought. We had lots of visual ambitions, but the weather was crazy. And so we met with a lot of storms and high clouds, but I was still able to image some and had a great time. Did not realize it until we were up there that Barcroft is on the slopes of the White Mountain, and the White Mountain happens to be the easiest 14er to hike in California. So on our way up, we stopped at the mandatory, bristlecones, and as you can see here, the road up is crazy steep and rocky, and the last 8 miles took us, I believe, over an hour versus the top here, where we were speeding along a one-lane freeway highway through a very curvy road. So it takes quite a while to get up there. But the bristlecones, they're some of the most ancient trees on the planet. And if you ever do go to Barcroft, it's a must-do to stop. And then the views up at the top of Barcroft, again, were spectacular. So the daytime activities on these trips are just as compelling and as fun as the night. So here we are at the top of White Mountain. This is the Instagrammable post here. We saw lots of animals, 3 different herds of acorn sheep. We also saw there were it was Marmot Valley. There were so many marmots around. And this is the reality picture. So this is me at the top, totally out of breath. Going from sea level to 14,000 feet is a little challenging. And if you didn't notice in this picture, when we left, they had said 20% chance of showers. On the way down, it hailed and thundered and lightning our entire way down. So perhaps we weren't the smartest to do this. We met up with a biker who also got stranded in the storm with us and all just hunkered in the rocks for a while as the thunder and lightning actually struck the observatory, the abandoned observatory, in Barcroft on our way down. So that was wild. This is us leaving the next morning. So this is not often melds well with astrophotography. So that was the typical weather. But I was able to set up my telescope. So I had brought my telescope, and seeing the weather, let's see if I could, yeah, there we go. Seeing the weather forecast, I threw in my lens at the last second because it has a larger focal ratio and I can collect light faster. So I dished my primary effort and decided to throw in the lens, even though the optics are worse. And I'm glad I did, because I decided I want to take a picture of the Iris Nebula and figured I would need 16 hours of integration to get an acceptable image, just by looking at pictures online. So I did take about 14 hours of images, and I used 3 of them. So I had 3 hours of acceptable subs, and I was able to get this picture. And you can see the Pleiades here. The Iris Nebula there. This is the Dangle-Hartle Nebula that we zoomed in on. Never heard of it before. It used to be thought to be an ancient planetary nebula, but it's actually a collection of ionized dust, I guess just H-alpha and O3. So that's right there in the image. We've got the rotting fish, the dark shark. I think this whole area is called the Wolf's Den, if anybody knows. Or it might just be this dangly dude here, I'm not sure. But here we've got the iris, and this guy is, that tiny guy there is the ghost. And then this, I guess, is the scorpion. So they have a lot of LDN numbers, but this whole part of the sky is in Cephas, so lots of famous neighbors around, just a fun, again, I think I'm addicted to space dust. So, so I was able to get some successful there. So this is my call out to all of you DSO. We have a quick question. Let's see if I can turn this on.
I don't know what merits the
Yeah,
microphone.
I know I'm not good at hosting and speaking at the same time, obviously, huh?
No, I just wanted to ask are these the true colors or are these with filters?
Yeah, no filters.
These are the true colors.
Right, I didn't not use any filters. Yeah. This is my call to all of you DSO, light collecting hounds out there. That dangle hardle, the ionized gases here. I guess this is a supernova remnant, very faint H alpha, and then that's that dangly dude that I think is pretty cute. So if anybody wants a less image target, there you go. Okay, after we came down Barcroft, we stopped at Mono Lake, and I was lucky. I got a picture of my first lightning. Took me about 20 minutes sitting there holding it. Again, lightning and astrophotography don't often go together, but I think it was worth it because I've never taken a picture of lightning, and that was handheld, and there were 3 flashes, and I just happened to get it in one of my frames. These are the tufas at Mono Lake. Is anybody familiar with the tufas? Yeah, so yeah, pretty amazing to see. Right here are the osprey getting ready to roost for the night or rest for the night, and then we were treated to a fabulous sunset. And then the next day, I met up with some other photography friends. So again, got treated to another spectacular sunset here. But this is the ghost town. It's just north of Mono Lake by Bridgeport. And 90% of the town is missing. I guess got taken down by a fire, but the downtown is still there. And I guess Bodie at one point during the gold rush had the highest murder rate in the nation. We went to the graveyard. I thought it was going to be cloudy all night, but it did clear up after midnight, and so I did get some images. While we were in the graveyard, the coyotes were howling. It was really spooky. I mean, they were howling. And then this is the mill. If you ever do go to Bodie, I recommend doing the tour of the mill. That was the highlight of the trip for us, just learning the history there. We had a really great guide, just cars and old buildings and just fun to walk around and see. And if you're a photographer, there's just so many treats there. And then I did the star trails. This is the Methodist Church. I wanted to preserve the star color because the other times I've done star trails, I didn't really know what I was doing, and it was just white. So I really wanted to make sure I got color, and then I wanted to represent it as accurately as I could. So I try not to adjust the colors too much. I don't know if I did a good job. I'm just really excited that I have the golds and the blues and the whites, for the different, heat of the stars. And then just this wide angle view, I was really glad I was able to frame it to get that spinning top sensation, kind of Van Gogh feel to it. So yeah, so that was fun. So that was my trip. Thank you again to all of the volunteers that make Mount Diablo great, that provide these trips for us and these great chances to interact with each other. And I'm just going to do a quick solicitation that this club is great. It's been great for over 50 decades because of the hard work and the commitment of members. And I really appreciate you all. We always need help, okay? It's time for the next generation to step up. Some of our members have been helping out with the club for decades. So if you're at all interested in helping out with the club, we have lots of positions available right now. Come hit me up. We would love your help. Small, any portion you can. We're all busy. I know I'm, always trying to struggle to get this in, but this club is wonderful. It's public outreach. You never know what lives you've touched, what children you've sent off, with a passion that they didn't have before they met you. So let's keep our club strong. Help out in any way you can. Give me a buzz. Thank you guys. Okay, we'll take a 10-minute break.
Pardons, there doesn't seem to be any vocals on Zoom.
Yeah, you do it. Okay, can you hear me now?
online? Everybody okay?
Thank you.
Okay. I'm going to mute this. That'll stop that feedback. Okay, so our main agenda tonight is coordinate systems. Here's a list: altitude azimuth and equatorial, which you probably are all familiar with. I'm going to maybe show you a couple things you didn't know about those. Then we're going to talk about the ecliptic coordinate system, the heliocentric coordinate system, the galactic, and the one I learned about when I was doing this presentation, supergalactic coordinate system. So I actually learned a little bit when I was preparing this, trying to be thorough. You're going to see how to operate a celestial sphere. So if you own one of these things, every time you see one in a Hollywood movie, they're only for decoration, and they're never, ever set up correctly. So I'm going to show you how to operate one of those devices. I'm going to explain a thing I learned yesterday, which is, why is it called right ascension? Is there some kind of wrong ascension? But I found out what right ascension means yesterday, and after all these years, you can still learn new things. You're going to learn how to find things on a star map, and I'm going to confess that I have been teaching a thing wrong for 41 years. So I figured it out, and now I'm going to teach it right, and there's a small tiny hands joke in there somewhere, so I'm going to tell you that joke and tell you the thing I learned that I'd been doing wrong all these years. So those are the exciting previews of what you're going to hear about tonight. All right, so astronomical coordinate systems seem to fall into three categories. You will probably notice there's only two listed here. One of them is the heliocentric kind of coordinates, where the sun is the vertex of all the angles being measured. The one that we're more familiar with is the one where the geocentric or Earth-centered coordinate system, where the Earth is the center of the coordinate system. And there's even one where you are the center of the coordinate system, your face, which we call the egocentric coordinate system. Now, that fellow there, his name is Doug, and he actually knows I use this slide as a joke, and he's quite proud of it. Anyway, so the teenager-centered coordinate system we use at the high school. So we talk about all three of those, and they manifest themselves in different ways. So first thing we're going to do is talk about the celestial sphere. And the celestial sphere is not just a toy. If you try to buy one on Amazon.com, they'll show you these things. You can buy a thing called a celestial sphere. It's a thing. It's a toy. So you can own one. But in astronomy, the celestial sphere is not just a thing, it's an idea. And the idea is, when you step out of this building and walk down the street and look around you, you'll see that there's trees and buildings nearby, and then you think about the Earth curling away from you. Despite what the flat earthers think, it kind of curls away from you, and wherever you go on the Earth, it feels as if to you as if you're standing on top of the world. So if you lived here, everything in the universe, everything in the world, that a place that you can go, the jobs you'll ever have, the property you'll own, it's all under your feet. And above your head is what they call the vault of heaven, as the ancients used to call it. And the celestial sphere is the concept that the sky looks like somebody put a bowl over your home location, and there's little twinkly lights in the bowl, which we call stars. So it's the idea that the universe looks like. It looks like this. And my students say, is it true that the stars are all the same distance from us on a ball? I said, and I say no. And they say, well, why do they make this thing that isn't true? And the answer is, it looks like this, but it doesn't mean it's built this way. And as you all know, it was a very long and complicated story, because we started with this, because it looks like this, and to figure out that it isn't really that way, and the stars are all different distances, and the stars are suns, and planets don't move in circles, and all those things is a very long story. And it's basically the story of the invention of astronomy, and in some ways the invention of science. But we still make these things because they're useful and that they mimic what it looks like, but they definitely don't represent what it is. And tonight in coordinate systems, we're more interested in what it looks like, so that we can visualize what we're pointing at and aim in the right direction. So no matter where you're observing, the first coordinate system anybody learns is that wherever you live, it feels like you're on top of the world. The people in Australia do not feel like they're upside down. I met a teacher from Australia once, and I interrogated her mercilessly and I learned a few things, that occasionally a teacher in rebellion will hang their world map upside down to put Australia on the top where it belongs. I also learned that Australian children often learn about the seasons being reversed in the northern hemisphere long before they get to school. I have to teach my teenagers, and they don't believe me at first, that the seasons in Australia are backwards, and we just experienced the first day of spring in Australia because the children in Australia watch American movies, and the American children do not watch Australian movies. So by the time they even get to school, the Australian children are asking their parents, I can't do an Australian accent, sorry. But why is it snowing in December? December is summer. And the parents have to explain to them that the Yanks think the whole world is just like them and they don't know the seasons are reversed in the southern hemisphere. So, everybody thinks they're on top of the world. And the entire universe revolves around them. That's the egocentric universe, You're the center. And that's what you experience. The whole world's experience comes through your eyes and your senses. And you're not thinking about it in the abstract, you're just outside experiencing the universe. This is an expression of that. It looks like that. Like the Earth is in the center, you're standing on top of the world, and your viewpoint is that viewpoint. So the celestial sphere is an expression of the idea that you're standing in the middle, there's some kind of a bowl over your head. One ancient theory declared that the vault of heaven was a lid, like a cookpot top, and it had holes in it, and the beautiful light of heaven was just leaking through the holes. So they thought the stars were holes in the lid, and that the planets, of course, were closer, moving around in front of everything, because you could see things such as the moon going in front of a star and blocking it off. Everyone was well aware that the moon was closer than the other objects, and closer than the planets, because the moon can cover up the planets as well. So there was at least some degree of three-dimensional knowledge, even from the most ancient observers, because you can just see it with your eyes. Anyway, my first little segment here is, I don't know if you have one of these around. They're not very common to have in your house. We have one at Deer Valley, you see here in the picture, that's about this big. It's museum quality, quite large. You see them in planetariums. We're very lucky to have one. This is my backup one. So if you ever see one of these, I don't know if you understand, it's not a very common thing to have, so maybe you don't know how to operate it. I'm going to teach you how to operate this thing. It's really, you might think of it, I know all of you know what planispheres are. This is a three-dimensional planisphere. It does everything a planisphere does. So I'm going to walk you through the steps of how to operate it. Now, does anybody here happen to know, in this room, at this place, which way is north? About that way? All right. So step one, the Earth's rotation axis spins like this, and it points at the North Star, as you probably all know. So you take the stick, and you aim it at the North Star. So you tilt the stick upward at an angle equal to your latitude. Navigation school day one. The altitude angle from the horizon up to the North Star, technically the North Celestial Pole, but it's pretty close, is equal to your latitude. So this is now parallel to the Earth's rotation axis. As the Earth rotates around its axis, the stick and the sky, everything rotates around it as well. So it's all lined up like this now. Holding it this way, you should be able to see that the place you live is now on top of the world. So that's step one. Point your stick at the North Star. Tilt it at the angle of the North Star. Here where we live, all of these towns in this area, is 38 degrees north. Okay, so the next thing is you rotate the globe. So you twist this knob here and you spin it so that where you live is on the top. So I'm putting San Francisco on the top of the globe. The Bay Area, you can kind of see where it is on the globe. You put that on top because that's where you live. The next thing is you reach inside. There's always a hole in the side of it. And if you're lucky, your arm fits. So you reach in the hole and grab a hold of this ring, which you flatten out. It has north, south, east, and west cardinal directions on it. So you flatten it out, and you put the north on the North Pole side. The gap in the bottom, which is there to get around the stick, is always the south side. And if you do that, that indicates that this is north, and that is east, and this is west, and that must be south. This ring is called the horizon ring. If it's level with your floor, it's like you're outside, and everything above the ring can be seen, and everything below the ring is below the dirt. You can't see through the dirt. So you can't see this stuff. We never see the South Celestial Pole, but you can see the stuff on top. There's a couple other adjustments that you need to make. Next, you have to twist the knob at the top. This is connected to the ecliptic pole. And at the end of the pole, there's a little yellow ball, which represents the sun. Obviously, the sun is not a small yellow ball. So this is just a marker to tell where the sun is. And if you look carefully, there's a ring of dates on the edge of it. These are the dates the sun is in front of those constellations. My first day of astronomy class is to point out what's your birthday. Oh, you think you're a Taurus? Let me show you. You're not really a Taurus. And so I upset some kids with that every year. It's tons of fun. So right over here, on this side right there, there's a black line of dates that comes down and crosses this crack in the globe. It's right there. That's a very important spot in astronomy right there. That's where the ecliptic, or the path of the sun, lines up with the celestial equator, which is where the Earth's equator is projected out into space. If you live in Ecuador, shine a laser pointer straight up, you're pointing at the celestial equator. So I've got the sun on the correct date, and I'm going to set it this way. Your final adjustment is to twist the entire sky with the sun with it until you get to a representative position showing where the sun is at that time of day. So if you're going to do it for a sunset, I'm holding it here, I'm twisting the entire globe, making the sun go up and down. Here's the western horizon right there, a little yellow ball on the stick. If I put the sun slightly below the western horizon, set it down and aim it north, I have now adjusted the device so I can do things with it. Everything now above the horizon line is visible now outside in the sky from this location. Everything below the line we can't see right now. So if we went outside, and if you could make yourself very small and get inside the dome, this is essentially a planetarium seen from the outside rather than being inside of it. So you could, the way my students relate to it, I mean, they can't do anything without a phone. I swear to God, they would suck soup through it and use it as a straw because they want to use that phone for everything. So I take one of their little phones and I stick it in this hole. And one thing that I have found that the modern generation is better at than mine was, they know exactly what a phone will see. You put a phone in a place, and they know what the phone's going to see. They understand the viewpoint of the phone. So you take the phone, you stick it in the hole, and you look around and say, this is what the phone would see. It's like you're inside the dome. And then I get oh, now I get it. Now in practice, these were not designed when phones were around. So what you're supposed to do is walk right up to it, put it in your face like this, and look through the part that's out of focus in front of your face and observe the other side. This is so blurry and out of focus you don't notice it. You read the other side. That's why if you look at it carefully, you'll notice all the words are backwards. So because you're not supposed to read the outside of it, you're supposed to pretend to be on the inside and look at it. So once you've made all these adjustments, you've got yourself essentially a coordinate system adjusted for your local egocentric universe as if you're on top of the world. And then you can look around with a phone. I stuck a phone in there and looked around. And here over Captain Kirk's shoulder, you can see the Big Dipper in the background, oriented the way it should be tonight, with the handle on the left and the North Star up and to the right from it. That's what it would look like now, if we went outside and looked at it now. So anyway, that's your little lesson on celestial spheres. And every time I see one, if it's in a public place, I always stop and adjust it. And now it's right. Okay, leave it like that for a couple hours, it'll be all right. So,
How long ago was that invented?
the original ones were not, of course, they didn't have clear plastic. So the ancient ones from the Middle Ages, they were solid, and they were printed so you could read the words on the outside, and it was very confusing to use because you had to figure out, okay, I'm actually, it's backwards up in the sky. It would look like the constellations were backwards to you. So that's a very ancient thing. I have no doubt Middle Ages or before, I don't know an exact date. But until you invented clear plastic, you couldn't make one of these. Now, as you know, the ancient Greeks thought there's earth, air, fire, and water. And the fifth element they thought was some crystalline sphere in space. So if you could take this into the past and show an ancient Greek, they'd say, oh, you've made it out of quintessence. It's from heaven. It's clear, transparent crystal like the heavens are made. Where'd you get it? So, if I was a time traveler, I think this would be worth a lot of money back in the past. All right. Now we're going to actually talk about coordinate systems. This, again, is the coordinate system that's egocentric, where your face is the vertex. All the angles are measured from your face. You're pointing at things in the sky. And this is called the altitude azimuth coordinate system. And every coordinate system has to have an origin where 0, 0 on a graph would appear. So as I describe these coordinate systems to you, I'm going to point out where the origin is, where the vertex is, and what symbols are commonly used to describe angles with them. You're probably familiar with this because many of our telescopes use altitude azimuth coordinates. So this little guy can tilt up and down like this. That's the altitude angle. And it can also turn left and right like this. That's the azimuth angle. So this beautiful little telescope, I really think the Questars are just works of art. They're just so beautiful. When you set it on a table like this, it's an altitude azimuth coordinate system. Now, the local coordinate system is based on your face. So locally, you would say, based on you, the point directly over your head is zenith. The point directly beneath your feet is called the nadir. And the astronomical definition is the horizon is not where the sky meets the ocean. It's a perpendicular plane that goes through your eyeballs, and it cuts that zenith nadir line in half. It's perpendicular to it. It's a perfect astronomical horizon. Often doesn't match. If you're on a mountain, for example, it'll be above where the sky meets the ground. And if you're on the ground, here where we live, there'll be a tree or a building in the way. So astronomical horizon is a perfect two-dimensional flat plane intersecting the zenith nadir line at a right angle and going through your eyeball. Whereas the more normal view of a everyday life horizon is where the sky meets the ocean at the beach. And if you're on the beach looking at that, it's very close to the same thing. We use the horizon in the astronomical sense then as a basis for measurement. We measure from the horizon. It's a definable location. You can find out where it is with a level held up to your eye. So the first thing you'll measure is the altitude angle. The altitude angle, you can imagine just a flat line coming out from your eye being 0. And then you tilt up and make an angle, like on a protractor. The angle goes from 0 at the horizon to 90 degrees, which is straight up, called the zenith. Those of us of a certain age remember zenith televisions. Zenith, the top, the best, the most, the highest, right? And the opposite of zenith is nadir. Nobody ever made a nadir television. So it's zenith and nadir. So can you tell me, what do you think it means if I said something had an altitude angle of -15? What would that mean? Below the horizon, you cannot see it, right? So we're going to practice. I'm going to show you something you might be surprised to find out. We're going to practice altitude angles. I'm going to see if you're better at this than my untrained high school students. We're going to practice pointing at altitude angles, okay? So I'd like you, as you sit there in your seat, to stick your arm right in front of you. Careful not to slap the person ahead of you. And then make it level with your eyeball. That's 0. And if you could just lift your arm to what you think is a 60-degree angle and just hold it for a second. Okay? I can tell now that as a group, you're generally speaking better than my high school students. But look around and you'll see that you don't all agree. I have people who are doing this, and I have people who are doing this, and a couple doing this. So you can relax for a second. If you do this with untrained people, and you're amateur astronomers, you know about altitude angles, you're familiar with it, and you've probably heard about all this before. I'm just kind of setting the stage for the new stuff. But you're pretty good at estimating vertical angles. Your average kid is not. If you say, hold it at 60 degrees, they'll go like this. And it's okay, what do you think 30 looks like? This? We'll count off by tens, and they'll go 10, 20, 30, 40, 50, 60, 70, 80, 90. Every time. You can train them. They'll remember for a week or two, then they forget again if you ask them later. I've even photographed them from the side. Hold up your hand to 45 degrees, and what do you think that looks like? I get beside them, take a picture, put it on the screen, put a protractor up there. See, you're not 45. You think you are, but you're not. There's a science fair project hiding in there somewhere. Untrained people are not good at estimating vertical angles. We tend to squash it all down because as much as we like to think we're descendants of climbing monkeys, we're really two-dimensional people. We don't go up and down a lot. At least that's my theory. Anyway, so altitude angles, that's how they work. They can't be higher than 90 because if you go past 90, you might as well turn around and go this way. So the biggest number you get is 90. We practiced that already, so I think it's okay if we skip that. I already said all that. Now there's azimuth. Okay, azimuth is a horizontal angle. We're going to practice that too. And for this, you're going to need to stand up briefly. So just everybody on your feet. Wake that kid up in the back. Okay, we're going to point at the origin of the coordinate system. Altitude 0 is right in front of your eye. And you said north is about that way. Let's just call it straight towards the wall is north. So you're aiming right at the wall directly in front of you, all parallel pointing. You're all at the origin now. That's 0, 0 on your graph plane. So I'd like you to rotate to azimuth 90. Where do you think that is? And then altitude 40 at the same time. Azimuth 90, altitude 40. Okay, so I think you folks need to be a little bit higher, just a little bit. The one in the back, you're too high, come back down a little bit. All right, and that's pretty good. All right, now go back to 0. We're going to do about 3 of these. You're going to practice. Careful not to slap anybody. Here we go. Can you estimate where azimuth 200 is, altitude 20? Where's that? Azimuth 200, altitude 20. 90 is east, 180 is south, go a little bit more, and then up a little bit, right? So that's good. That's good. Now turn back to the front. Let's do one more. So if you were trying to explain to somebody, you saw a meteor, you saw a UFO, you saw whatever, and you're trying to tell them where it is, these are local coordinates. Everybody near you will agree on approximately what the altitude and azimuth is. Of course, it's a round planet. So if you talk to someone in another state on the phone, and they're not going to agree with you what the altitude and azimuth is because the Earth is round and their ground is tilted with respect to yours. But anybody who's near you will all agree that's the altitude and azimuth. Let's do one more and you can have a seat. Okay, so for this one I want you to do azimuth. Oh, let's do 300, altitude 80. Where's azimuth 300, altitude 80? Oh my gosh, you're so much better than my high school kids in this. So yeah, pretty much everybody's got the right idea. It's but you're too low for 80. Go higher. It's a little higher. A little higher. A little higher. It's almost straight up. Okay, that's about right. Okay, relax and have a seat. The advantage of the altitude azimuth, or alt-az as we sometimes call it, right? It's simple. It's simple. The big disadvantage is that it's entirely local. So this person and this person don't agree on the coordinates because their horizons don't line up. That enables you to do things like parallax. I have coordinated with a teacher in Wisconsin. We both took photographs of the moon at the same moment, coordinating by cell phone, and the moon was not in the same part of the sky for us at the same time. The altitude and azimuth was completely different. We did that, so I can skip through that. Now let's see, I'm going to do some demonstrations. I already did the telescope mount. I want to show you this little app I have called Theodolite. It's not really an astronomy app, but it's a handy one. Theodolite, Theodolite. It's on the bottom bullet there. So it's an augmented reality app. It takes your phone's camera and overlays a grid. It has on it altitude and azimuth angles. So it tells you which way you're facing. Now, like all such apps, I'm sure you're familiar with other astronomy apps that point at the sky. It needs calibration. It's not perfect, but it's pretty close, and it's better than guessing. So if you wanted to say, okay, I'm trying to tell, like I saw this thing in the sky, and I want to give you a rough direction. Right now I'm pointing at azimuth 150, altitude 30. My phone is pointing in that direction. So that you can get a somewhat more precise measurement off of the Theodolite app. It also gives you the exact time down to the second, which my clock doesn't do, and it tells you your altitude above sea level through GPS. So you can, it's a little navigation tool, kind of cool. And when you're traveling, going to the top of a mountain, and that's kind of nice to see what your altitude is without having to look at the signs on the road. So there's that demo. And then, of course, our favorite astronomy program, Stellarium. I don't know what your favorite is, but that's mine. It will do altitude and azimuth coordinates. We're going to do a little demonstration of that to show you how to see them. So I think I'm sharing my entire desktop, so you folks online should just see, whatever I see. I'm not sharing the window, I'm sharing the desktop, so everything should still work. So this is my favorite program. It's free. I'm sure a lot of you have used Stellarium for one thing or another. One time, just to say I did, I managed to make my telescope connect to it and control it with a telescope. I use it in our planetarium at Deer Valley. I designed from a plans I found online, a reverse hemispherical projector system, and built it from a classroom projector, a mirror I bought, and this software on a spare computer, and now I run the planetarium off of it. It will distort the image and make the picture come out all straight. It's really kind of cool. But on the desktop here, you can see a bunch of stars. Down at the bottom, as you may know, there's a bunch of functions. And this is the azimuthal grid. You turn it on, and you can see the altitude azimuth coordinate system. Therefore, the zenith will be where all the lines converge there at that point right there, near Vega right this time of year. And then down below, you can find the azimuth numbers. And as you may know, if you point to a target in Stellarium, it will give you a bunch of information. So right now, it's actually telling me the altitude and azimuth, and it's changing continuously because it's simulating the sky in real time. So if I stop the clock, you can then see the numbers that appear there. So my students do labs with this information. So I, for example, have them point at the sun and measure the altitude over a day, the azimuth over a year, collect data tables, make graphs and stuff like that. But if you're interested in obtaining those numbers, you can get really good numbers for a simulated lab and do it in a few minutes instead of waiting a whole year to do it in the real world. So altitude and azimuth information is built into any good astronomy program. If you want to know what it is in a simulator, it'll tell you. Do remember, though, this is a simulator and it's not real, but it's really accurate. Yes, sir. Oh, yeah, yeah. When I tried it, my students have to do an observing notebook. And oh my gosh, I'll tell you how many times I have to tell them, don't draw the computer screen. Go outside, look at the real world, use the computer to figure out what it was. And they're saying, oh yeah, I saw NGC 7465, and I saw the rings of Saturn with my eyeballs, you know, because it was on the screen, you know. And I have to be diligent about them they're just trying to do it on their phone at night in their basement and not actually go outside. So anyway, that's the altitude azimuth system, and we have several others to talk about, and I'm going to move on. I think I'm done with that. Next. Here's the thing. I told you I learned a thing, and I've been doing it wrong for 40 years. Here's the thing. For 40 years, I've been teaching my students that if you do this trick, which all of you probably know, you probably knew I was wrong and didn't tell me, but you take your hand like this and stretch your little finger and thumb out as far as you can. This is what we call the astronomer's gang sign. You lock your elbow, and you hold it up in the sky. You can use that as an angle measuring tool, right? I was taught many years ago that is 20 degrees. 20, 40, 60, 80, 90, right? 20, 20, 20 degrees. And it occurred to me that I never actually bothered to find out if it's actually 20 degrees. So either I've been teaching it wrong, I've got really tiny presidential hands. Because I measured with a ruler, or my wife did, she helped me out. I measured this, I measured that, did a little trig problem down there. My hand's only 14, almost 15 degrees wide this way. And I thought it was 20. So now I got to say, either I got small hands, there's another science fair project. Measure a whole bunch of people and find out what it really is for the average person. Because, you know, some people have big hands, some people are the president, and, you know, it's like that. So anyway, and this is supposed to be 10 degrees, and your fingernail is 1 degree, and it's about twice as big as the moon, and nobody believes it till they try it. So you can use your hand as an angle measuring tool. And it comes in handy sometimes. For example, when we go to a parking lot we've never been to before, my wife says, "Where do we park, Mr. Astronomy Guy?" And I say, well, let's see. The sun's over here. We're going to see a movie. You're going to be in there for 4 hours. The sun moves 15 degrees every hour. Boom, boom, boom. When we come out of the movie, the sun's going to be over there. That tree will have shade right here, and that's where we park. So that is my secret amateur astronomy superpower. I can tell where to park. So here's my van, and that's where I park when I drive to work. I don't drive every day, but when I drive, I park right there because the sun is there in the afternoon when I get off work, and it's always in the shade and it's not so hot. And you can use the angle measuring tool and your knowledge that the sun moves 15 degrees a day and predict good parking places in advance. So there's that. Just a summary of all the things I just said. The meridian is on there. It's a line that goes from north to south. You probably know this already, but when the sun hasn't yet reached the meridian, It's before the meridian. In Latin, that is antemeridian, which is abbreviated AM. And after it crosses the meridian, in Latin, that's post-meridian. You abbreviate that PM. So when I teach it to my students, they've been saying AM and PM their whole lives, never knowing what it stood for. They just memorized it's the same name as that convenience store. When I was a kid, I memorized it as after midnight and past the morning. I remember asking my teacher, what does AM and PM stand for? They said, it doesn't stand for anything. It's just remember it. Just memorize it. And that's how I memorized it. But now we know. Here's the last slide on altitude azimuth that shows the coordinate system. The horizon and the meridian form the intersection that you pointed at earlier. That's 0, 0. And that's a summary of everything I just said. So we're just pointing out that we're going to do the same thing for all the other coordinate systems. And I will not be talking so long about them. It goes a little faster. So let's move on. The one that's probably more important to you and more interesting is the equatorial system. This is what you refer to as right ascension and declination. And oh, by the way, I don't have a slide for this. I'm going to tell you. I learned recently what right ascension actually means. Why is it called right ascension and not wrong ascension or whatever? So if you go to the equator and you watch objects rise on the eastern horizon, they'll rise straight up. The moon does, the sun does, all the stars go straight up. And they are at a right angle with the horizon. And when they go from the horizon up, they ascend. It's right-angled ascension. Now, where we live, we're not on the equator, so when things rise, they come up at an angle. That is known as oblique ascension. And it's a term that is no longer used. It's obsolete, kind of medieval. So we kept the right ascension for our maps, and we forgot about oblique ascension. But that's the origin of the word, which I never knew until yesterday. Anyway, the coordinate system here has a different reference line. It's not the horizon. It is the celestial equator. You take the Earth's equator, you project it out into space, like with laser pointers. You're pointing at the celestial equator. Another way that you can find it easily is to point at the North Star, make a right angle with your arm, and now you're pointing at the celestial equator. So you can point to it even if you can't see it. And in our celestial sphere model over here, the celestial equator is the crack between the two spheres where they're glued or taped together here. That's the celestial equator. It's directly above the Earth's equator. Like the equatorial system is called that because it's lined up with the Earth's equator. And like the Earth has a north pole, so does the sky. So you just tack the word celestial onto everything. The north celestial pole is above the North Pole. Stand on the North Pole, look straight up, there's the North Star. The south celestial pole is down here. Look straight up from the south celestial pole. You won't see anything because there's no South Pole star. Southern Cross is kind of nearby, but not that close. So it's just like you took the Earth and projected its coordinate system out into space. Now, because the Earth has longitude and latitude lines, if you project those out into the space, you could refer to those as sky longitude and sky latitude, and that's technically, conceptually what they are. But they have other names. The sky latitude is called declination. It goes up and down from the celestial equator. The sky longitude is called right ascension, and it goes left and right along the celestial equator. Now, you need to have an origin for any coordinate system. And so I'm going to explain where the origin is. And it's a really good day to do it because it's related to the equinox days. So the ecliptic is the path of the sun through the constellations. The constellations it passes in front of are known as the zodiac. But the sun itself actually takes a linear path through those. It's a line. So we define the ecliptic as the path of the sun going around the constellations. It's a line. Now you might think, here in this picture, the ecliptic looks like an oval. Why don't we see an oval in the sky? Why do we see a line? The answer is because the solar system is flat and we live in it, not above it. So if you imagine the classic picture of a solar system with concentric circles on a poster, you cut out the Earth and you put your face in the poster and look around, all the planets and the sun and the moon will be all confined to that poster and it will look like a flat line to you. So we don't see the concentric circles you see in school books, we see a line because we're in the picture, not above it or below it. So the ecliptic is a line. The catch is that line, representing the path of the solar system, is not lined up with the line for the celestial equator. They are not parallel. They're tilted. So just to be blunt about it, if this celestial sphere represents the north celestial pole, and that pen is not very good. Always have a backup plan there. That's a little better. That's the North Celestial Pole. This is the celestial equator around the edge like that. And that's the equatorial system. It lines up with this globe like this. And then at the same time, we have the ecliptic system. This is the path of the sun through the constellations along this path. And this spot right here represents that knob. That's the knob that turns the sun around in a circle. So the two spheres don't line up like this. They're not like this. They're like this. They cross. They cross here, and they cross here. The two equators, the two lines cross here and here, right? One of them, where the sun is going towards the celestial equator and crosses north, that is the vernal equinox, the first day of spring. Yesterday, the sun crossed the celestial equator heading south. It was here on the other side. That was yesterday. So the reason that those are important points is that the coordinate system for the equatorial system has to have an origin, and they picked that spot right there. That is where the celestial equator crosses the ecliptic, and the sun is heading north, not south. The first day of spring. The location of the sun on the first day of spring is the origin, 0, 0, for that coordinate system. On this globe, that's right here. So this is the path of the sun. It's in black letters, kind of hard to see from the back, but there are lines going this way with the dates. Here's the equator. And right there, if you look at it, it says 0 hours right ascension. That's the origin of the coordinate system for right ascension. It starts there. The stars are glued to this coordinate system. Unlike the altitude azimuth system, the numbers are constantly changing. I had to stop the clock because the numbers were changing. They don't stay the same throughout the night. So in this system, the stars are glued to the system, and as the sky rotates, it takes the coordinate system with it. So the right ascension, the declination of the star doesn't change. It's always at the same number. The numbers, they do change very slowly, but for the purposes of casual observing, they don't change much during your lifetime. So that's where the origin for the system comes in. You can see the ecliptic. If you can see a couple of planets in the sun and the moon, you can see the ecliptic. You just connect the dots. So if you see the sun over here, and I've turned off the atmosphere, I know that's not realistic, but just to make the point, you can see the sun over there, there's the moon, over there is Jupiter, and there's Saturn. If you connect the dots, you are pointing at the solar system, you're pointing at the ecliptic. After having taught this lesson, one year, many years ago, I had a student named Joseph Kopser, who, that kid's almost as old as I am. That's one of my first students ever. So Kopser was at a star party with me, and I had just taught this lesson. He goes out and he runs up to me, and he grabs me over the shoulders and starts shaking me like this. I see it, he said. I see the solar system. And he goes, it's right there. So I never had a kid so excited to point out the ecliptic as Joseph Kopser. I still remember that to this day. He's like, I can see it. I can see it's flat, and we're in it, and there it is, And he goes all the way around, and I'm pointing at the Earth now too. We're in it, see? And it was pretty fun. Unfortunately, it only happened once. Here's a drawing to show the thing I just showed with the plastic spheres. The symbol here is the first point of Aries, the ram. In ancient times, that constellation was at the vernal equinox when they invented the system, and of course, because of precession as the Earth's axis wobbles, it's now shifted. That's why none of the constellations match up your birthday anymore. But the vernal equinox is right there in the middle, and that's where 0 is. And of course, the angle is tilted because the Earth's axis here, as you see in this globe, is tilted 23.5 degrees with respect to how it moves. So it moves this way, but it's tilted like. That's why they sell every globe ever made is tilted 23.5 degrees. It's mimicking that angle of tilt. And it causes the ecliptic to be tilted with respect to the celestial equator exactly the same amount. Okay, let's see. That's a special point. It's not only the origin of the right ascension system, it also marks the first day of spring, the vernal equinox. And I've already shown you on the celestial sphere what that looks like. Now, the right ascension numbers then start at the vernal equinox. And now if you look at this, as the sky rotates, it rises in the east and sets in the west. So it turns this way. So if you start from the vernal equinox and start counting to the left, because that's how many hours away it is as the sky rotates to bring it back to the same position. So something that's at 6 hours right ascension will take 6 hours to get where the vernal equinox was. Say the vernal equinox is on the meridian, and something has 6 hours of right ascension. That means 6 hours later, that object will be on the meridian. So that's a very important number for astronomers, because when the objects are on the meridian, it's the best time to observe them. So they're very interested in how many hours is it away from the meridian, right? So it counts to the left because the sky moves to the right. The numbers are increasing as the sky comes up in the east. And it's counted by hours because we're interested in the time we have to wait until our target is in place. That's why we don't use degrees for the right ascension numbers. We use hours because we have to wait until the right time to observe. When it's on the meridian, it's the best time to look at it, as you all probably already know. So on a star map, and I have some of these for you, so you can take one if you want. I don't know if I have enough for everybody, but I got a bunch. So these are some really old school SC1 and SC2 constellation charts. They're from Sky Publishing way back in the day. So if you want a copy of a star map, take one and pass it on. And notice how the numbers do progress around the clock clockwise. They go around clockwise to establish that. I don't think that's me. Okay. Now I'll teach you another thing you might not have known. Since you're measuring an angle in hours, you have to subdivide it to get smaller angles. So by ancient tradition, they cut up the hour of right ascension into 60 pieces, and they called those 60 pieces the first minute part of an hour. It was originally called the first minute part. And then when we invented the telescope and we could see, Tycho Brahe was famous because he could measure things to the first minute part of a degree. So in hours, we divided it up in 60. We eventually devised our clocks to mimic that pattern. And then each of those minute parts was then magnified with telescopes and chopped up into another 60 pieces called the second minute part. We got tired of saying all those words, and we abbreviate that as the minute, which used to be minute, and the second minute, or just the second. So minutes and seconds are based on chopping it up into the first part and chopping it up into the second part. That's where that word comes from. So in right ascension lingo, you have to mark those out and tell that they're not degrees. As you can see in this picture, 2 hours of right ascension is this big when you're near the equator, but when you're closer to the pole, 2 hours of right ascension is that big. It's the same angle, but it's not the same angular distance in the sky. So unlike degrees, which are always the same size whichever direction you point, right ascension angles, they vary in size depending on the celestial latitude or the declination. So in other words, the physical distance you move your telescope is less when you're near the celestial pole than when you're near the equator. And to distinguish those and make sure we don't confuse them with degrees, minutes, and seconds, we use a different symbology, which you may already know. Right ascension's hours with an H, minutes with an M, seconds with an S. So if you see HMS, we're talking right ascension and not degrees on a protractor. So we use a different symbol for that. And declination, this is perfectly ordinary angular degrees on a protractor. Don't change size as a function of angle. So you can just use a protractor to measure declination, and those use the traditional symbols, the little circle for degrees, 1 apostrophe for minutes, 2 apostrophes for seconds, right? My students used to get confused and think that was feet and inches, but they don't know feet and inches anymore now, so they don't get confused. They just learn this okay, they know minutes and seconds and declination better than feet and inches now. So anyway, those are the symbols that stand for right ascension to declination. Okay, let's see. I talked about the first thing. I showed you the grid marks on the globe are the same as the grid marks on the sphere. That's because this is sky longitude and latitude. This is Earth longitude and latitude. I want to show you in stellarium. Usually my presentations have an interactive part that's about to happen where you're going to do something for me. And then the second half of it is much quicker because I don't have as much to say. This is the most important one for astronomers because your telescopes are built with right ascension and declination built into them. But let me just show you a couple of real quick demos. So here's the stellarium again with the altitude azimuth grid turned on. Now we're going to turn on the equatorial grid and overlap it. So this must be the North Star where all the lines converge. And you see how they don't line up at all. And the convergence point is not straight overhead. Turning off altitude and azimuth so it's not so confusing. Now we see I did the wrong one. This one and not that one. So the right ascension lines are the long lines here. These are the right ascension lines, the sky longitude. And then the circles represent sky latitude. So you can see here 10, 20, 30, almost 40 degrees. That's the altitude of the North Star. So the circles represent declination, the lines represent right ascension. And it's just another grid, and we now know what the origin is, and the vertex is the Earth. The Earth's the vertex where all the angles are measured. All right, let's see. So your stellarium map will do both, your telescope will do both. So if you have one of those fancy new digital telescopes that I have one that I get to play with, it's almost always an altitude azimuth telescope because the computer has to convert the right ascension and declination to altitude and azimuth and point and tell it where to point. But if you have a more traditional telescope, you'll more than likely have a, if I can remember which one of these goes where, this one goes here, and then these two go on the side like this. One goes here. Oh, that was smooth. Anyway, this telescope is actually meant to be equatorial. So you put these legs in like this, and you set it on the tabletop. You can adjust the length of the third leg to make it whatever angle the North Star is. So now the clock runs around the rotation axis. As many of you have equatorial drives, you know, you aim the axis at the North Star, and well, technically the North Celestial Pole, and go through some effort to get that exact precision so that makes your telescope track better. And now the motor runs around here in sidereal time, turns around once in 23 hours and 56 minutes, and keeps up with the rotation of the sky. So now I've shown you that. And there's one other thing I wanted to show you. Before you leave tonight, somebody's going to walk out the door with this very nice, brand new, never been used, Tyrian SkyLS 2000. A laminated star chart with holes in it. You can mount it in a book. I don't have the book with it. It didn't come with the book. I just have the pages. But it's marked, of course, in right ascension declination. It's black, so you can use it in your observatory and not ruin your night vision. So if you don't have a really good star map, I'm going to give this away to somebody before I leave today. Trying to clear out the shelves before I retire. So I'm giving stuff away. And I have something else while I'm talking about it. I don't know where I got this. I don't know why I have it. But I've got a whole box of empty 35 millimeter film canisters. So swear to me, you will take one of these for every telescope you own, and I know some of you own a bunch of them, because these are great dust covers. You take that eyepiece out and pop that in, it blocks off the dust, and so I'm donating as many as you want to take. I have way more than you need, so help yourself to that. Let's see. Oh yeah, so let's go back to this. It's time to do our little activity. This won't take too long, I don't think. So we're going to practice your right ascension and declination skills. For this, you're going to need a handout and a pencil. I brought some pencils. I have handouts for everybody. So the mission is to plot right ascension and declination coordinates on a map. And if you plot all the stars, you'll find an easily recognizable constellation. Once you figure out which constellation it is, you come up here and show it to me. I give you a sticker. So let's get these passed out. I do need to talk, just pass them across. I'm going to have extras, I'm sure. I need to tell you how to set up the grid because the grid is blank. If you need a pencil, come up front and grab one. I brought a couple of boxes of pencils. Take one and pass them on. Here's some more. I don't think I gave you enough. And then some for you guys. And hit those people in the back row too. Sorry. Okay, I'm going to have mercy on you because our time is short. You need to set up a grid that all the numbers fit. So if you set up your grid as follows, darken a line across the middle, that's the celestial equator. Every dot I have you plot starts at 5 hours. And remember, I told you they can't increase to the left. So that's 5 hours. This is 6 hours. There's 10 boxes, so every box is 6 minutes. So if I did 5 hours and 18 minutes, That's 5 hours and 6, 12, and 18 minutes is right there. 5 hours and 20, maybe about there. 5 hours and 30 is here. 5 hours 45 is about there. So you're going to need to estimate going to the left where the scale is 0 to 60 minutes and write Ascension. Declination is simpler. 0 is in the middle. Count by 2s, 10 to the top, 10 below. So you go over X, you go up Y, you put a dot. There's 7 dots. When you're done, you'll have a picture, and I'll bet you recognize it. Let's do the first one together. 5 hours and 55 minutes. There's 5 hours. That's 5 hours and 54 minutes. So you go just a little farther, and that would be 55. The declination of the first one is positive 7 degrees. That's 2, 4, 6, 7.5, because it's 25 minutes. Put a dot right there. That's your first dot. Everybody follow that? I'm going to do that first one again. So first of all, it's 5 hours, so you start over here. 55 minutes. And again, these are 6 minutes each. So this is 5 hours and 56 minutes. That's 6 hours there. So this line is 5 hours and 56 minutes. You want 5 hours and 55. Did I say that right? 5 hours and 54 minutes. This is 5 hours, 54 minutes. You want 55. You go 1 more minute past, just a little bit past it. If you're a little off, it'll still work. And then you go into declination is the y coordinate, 7 degrees. And you go by 2s. 2, 4, 6, 7. And then a little bit more because it's 25 minutes is almost another half a degree. So right about there is your first dot. Okay? So plot away. If you successfully identify the constellation, I have for you a sticker from NASA, the New Horizons Space Probe mission, useful for putting on your laptop lid to keep it from being stolen. And then I've also got a few of the Fermi Gamma Ray Space Observatory. So these are left over from various workshops I've participated in. And I got enough to hand out a bunch. So plot away, all right? Feel free to split up the work. You do the first 3, I'll do the second 3. We'll copy each other's homework. So take a couple minutes and plot that out. 5 hours and 25 minutes. 6, 12, 18, 24, 25 is right about there. Almost halfway. And then go up to declination. Let's see what you think it is. No. Well, you know what it's called, right? What is that? Have a sticker. They're rolling in. Take your pick. Excellent work. Have a sticker. And a film canister if you want one. I don't know where I got 400 film canisters. I just found them in a box. I don't remember getting them. There's just 2 different ones. Pick the one you like. Hang on to them. Yep. Because actually, put your name on it. I'm going to use them for a drawing to give away the big star map. If you want the big star map, put your name on it. Put it right here. Okay? Looks like you got it. Yep. So grab a sticker and put your name on that and put it here. We're going to have a drawing in a minute. Yep. I have one big star map to give away. I've never used it, so I figured it'd be better in your hands than mine.
I have a question.
Yes.
Just to make sure I understand, this coordinate system is a specific The 0, 0 is a specific dot on the.
It is. It's where the ecliptic, where near you're pointing to it almost.
So it's fixed.
It's right
It's
there.
fixed?
That's a 0, 0.
It's fixed. It's always near this star.
It's always next to that star. That's correct. And incidentally, I don't know if you noticed this, but when you figure out which constellation it is on the celestial equator. So if you see that constellation, you know where the celestial equator is. It would be, yeah, so you're looking, it's a winter constellation, so it's going to be, let's see, 5 hours, right? So we can do it with coordinates. That's why we have maps. 0, 1, 2, 3, 4, 5 hours, and it's right there. So look in front of my hand. Look through it and look at my hand. See it?
Yeah, that's Orion, but the 0, 0, where is it?
0, 0 is right here. Oh, this is 0, 0. 0 is on this side. 0, 0 is right there. See the 0?
Yeah, so constellation is there.
Yep. Okay.
Pieces? Near pieces?
Feel free. 0, 0 is right there, and you count 1, 2, 3, 4, 5, and you'll find Orion. That's 2. Keep going. 3, 4, 5, and there's Orion right there. All right, you found it? Okay. Put your name on it, grab a sticker, and put it in the drawing pile. They're just 2 different kinds. So. We recognize it anyway.
Where do I put it? Oh, yeah, thank you.
Have a sticker, sir. If you want to be in the drawing, put your name on it. I'm going to have a drawing for the star map. Okay, how we doing? The drawing comes at the end.
Must be present to win.
Yeah, pretty much. Let's see. Looks like you got it. You squished it because this is like 5 hours and you treated it like 6. If you stretch it out, then you have the picture. Look right here. There it is. It's right there. Right in this area right here. So you did it right. You just squished it horizontally. We'll take it. Yeah, that's fine. So put your name on it if you want a drawing. Right here, have a sticker. That's okay. If you want to be in the drawing, you got to put your name on it, though. I'm gonna draw it out to give away the star map. All right, fantastic. Oh, good job. Have 2 stickers. Thank you. All right, now let's go back to the PowerPoint. Time is short, so I got to kind of fly through the rest of this because I don't want to keep you past our scheduled time. Let's see. And that was the long one, so we can take it from there. All right, there's that. And we're back. So there's the origin of the equatorial system, where the right ascension declination lines meet. It's the celestial equator and the ecliptic collide, and that is 0, 0, which I showed you on the globe. Symbolically, HMS for the hours, minutes, and seconds, and sometimes in angles. They don't use theta for this in astronomy, use alpha and beta. Alpha is right ascension, beta is declination. But usually people just write hours, minutes, and seconds, and degrees, minutes, and seconds. Sidereal time is related to that. This is a neat little website I found, and I'm going to post this entire presentation on my website, astronomyteacher.com, so you can download the presentation and the handout there. It's not there yet because the school blocks me from updating my website, but I'll do it in a day or two. Anyway, so you may have heard the term hour angle. Hour angle is measured in right ascension hours, and it's how many hours the object is away from the meridian. Then if the vernal equinox is here, the right ascension goes over to there, and then you come back here, and that's the hour angle. The difference is called local sidereal time. So this is a neat little interactive website where you can change the numbers on all 3 things and watch how these things interact. So if you've ever heard of hour angle of 0 good, hour angle of 6 bad, because that means it's on the horizon and not good to look at, right? Hour angle small good. Now we do ecliptic coordinates. This is the part where we speed up and just kind of fly through the rest. If your coordinate system is not centered on the celestial equator, but instead you tilt it and line it up with the ecliptic, it's called the ecliptic system. Who would need that is people who are navigating spacecraft. They want to know the ecliptic coordinates because it stays in the plane of the solar system. And it's only basically one coordinate you need to keep track of because everything's flat, right? So there are people who use the ecliptic coordinate system. Also, we use it to define axial tilt. So if they tell you like Jupiter is tilted 3 degrees, what are they measuring the angle with respect to? The Earth's ecliptic. So the path of the sun through our sky is the reference plane for the solar system. So axial tilt of planets is measured with respect to the ecliptic plane. In this system, the vernal equinox is surprisingly the same origin. It's just the entire system is tilted over. And you use the ecliptic pole on our celestial spheres where the knob is. The dates that you can see when you're standing next to it, you can't see them from the back. But the dates make a black ring around it to show the ecliptic. So the origin of 0, 0 is in the same place as it is for equatorial coordinates. It's just that the entire system is tilted slightly. As you know, the Earth's axis is precessing, and that means the coordinates of right ascension do actually change as time goes by, but only a very little bit. It's moved about 15 degrees since the invention of astrology, and that's why the constellations aren't lined up with your sun sign anymore. But over your lifetime, it'll change a few minutes of arc, and that means that the exact precise coordinates you might need for a giant telescope will be out of whack. So typically you'll publish a map like this one that Will Tyrion did. Is called Epic 2000. It was the coordinates in the year 2000. And typically, back before digital maps, they would publish new maps every 25 years or so and base it on 1975 coordinates, 2000 coordinates, and so on. So that would tell you what the coordinates were in that year, and they're probably pretty close to that now, but every now and then you want to update your coordinate system because the equatorial system is actually drifting very, very slowly. It'll come back to the same place in 27,000 years, but you know, over the course of a human lifetime and a giant telescope, it makes enough difference that you got to keep track of it. So if you ever see something like J2000, that is the year that the coordinates are aligned with what the sky was doing in that year. And they're slightly different now, but it'll probably be good enough for a backyard telescope to point at the object. It'll still be in your field of view more than likely. The origin here is the same as it, except that now I've tilted over the equatorial system and made the ecliptic system flat. So you can see the origin's the same place. The sky longitude, represented by lambda, is left and right. That corresponds to sky longitude. And then beta is sky latitude, ecliptic latitude, which is above and below the celestial equator. And again, the knob on there is ecliptic latitude of 90. That's where that knob is. I told you that already. Heliocentric coordinates. If you don't use the Earth as the origin of the ecliptic system, but you use the sun, the numbers are slightly different. And that's what spacecraft navigators need because they're trying to track the motion through the entire solar system. So there's actually several flavors of ecliptic coordinates. Heliocentric, Aries ecliptic is the one I've just described. The origin is the first point of Aries, and it goes along the ecliptic. And that's what astronomers would tend to use more. And also people who navigate spacecraft would use that more. But there's other ones that are based on the inertial mass of the sun, the center, the barycenter of the system, that's balanced between mainly the sun and Jupiter. And there's a bunch of obscure ones that are used for specialized purposes, but they all basically count along the ecliptic to get their coordinates. This is interesting. If you use heliocentric coordinates, you can in fact figure out how to plot the orbit of a superior planet. Back in the day, people like Kepler did it first. How do you plot the location of a planet when you can't use radar on it and you don't know how far away it is? You have to triangulate on it, and that means you have to wait one synodic period. There's a word for you. The synodic period is the time it takes a planet to return to the exact same spot in the sky. It's not the orbital period, because it's a combination of both the Earth and the other planet. So the Earth going around like this, the other planet, for it to come back to the same place in the sky, you have to wait a different amount of time. It's called the synodic period. The people in medieval times who did astrology were aware of the synodic period of planets, and Kepler basically said, if you wait one synodic period, the Earth will be in a different place, but the planet will not. So you observe the planet like Mars from two different places. You see what constellations are behind it. As you see in the upper right-hand diagram, Mars will appear to be in two different directions as seen from the Earth on the same synodic period. So you can triangulate on it and figure out where it was. There might be several years of time between the two observations. And to do the complete orbit, you have to go all the way around. It might take you 30 years of observations to get enough triangulated spots to connect the dots, as you see in the bottom right-hand corner. Now, I learned about this back in the Sputnik days. You know, we reacted to that by increasing funding for science education in the United States after Sputnik was launched. And so a lot of money flowed, and a lot of old school planetariums were built in high schools, and a lot of people started rocket programs. You know, even the Astronomical Society here was founded on the idea of watching Sputnik at first. Remember? I think you probably heard that story. You guys started out as Sputnik observers, and it turned into an astronomy club later. So one of the things that came out of it is a program called Project Physics. It was a series of workbooks that worked you through authentic astronomy activities. And I did that as an exercise as a student, early astronomy student when I was young. But since then, the book has gone out of print, and it came along with a bunch of photographs of Mars and grids that you could lay on it to get the coordinates. But I realized that you could recreate it if you used a simulator. So I used the same dates, and I created a worksheet. I borrowed some work from this lady who said I could use it with permission. And I recreated the Project Physics plotting the orbit of Mars using heliocentric ecliptic coordinates. And I have instructions. So you can, if you have a simulator, you can either look at the right ascension and declination and plot that, or you can look up the ecliptic coordinates, because Stellarium will do now. It has now added ecliptic coordinates on it. And if you do that, you can draw a circle, measure the angles, draw the lines, and plot Mars's orbit and get the actual eccentricity of the orbit, its orientation, and the longitude of the ascending node, and a whole bunch of other stuff, and do it the way the ancients did it, from scratch by hand. And I have instructions. So it's a rather involved project. I had 6 kids work on it for 2 months, and they did it. And I have a little poster where they plotted the orbit of Mars, and they got a pretty good answer. So if you're interested in what can I do on a rainy day with my simulator and actually do some serious astronomy, you can do 30 years of work in a couple of afternoons, or maybe 3 or 4 afternoons. But if you want a copy of that, that's up here for you. And it's a really good example of ecliptic coordinates and what they're useful for. Moving on. Here's the summary of ecliptic coordinates. The origin here, as you can see, I'm pointing at it. On the first day of spring, the sun is crossing the celestial equator. See the big yellow spot? The celestial equator is labeled there. The ecliptic is the tilted pink line. The intersection is where the sun is. It's at the origin for both the equatorial and the ecliptic system. Now we move on to galactic coordinates. This is something that you're not likely to use with your backyard telescope. In galactic coordinates, you line up your coordinate system with yet another great circle in the sky, and this is lined up with the plane of the Milky Way. The origin, I think, is fairly obvious, is the center of the Milky Way, known as Sagittarius A star, the giant black hole that is technically right at the center of the geometric center of the Milky Way. That is located here, I think in the inset picture. If you can see it well enough, it's kind of small, but that's Sagittarius. And there's the little spout for the teapot, and it's just off the edge of the spout of the teapot. That's the center of the Milky Way galaxy and the origin of galactic coordinates. In the galactic coordinate system, you see in the larger picture how it is tilted completely differently than the equatorial and the ecliptic coordinate systems. So it's yet another great circle. Basically, if you can see the Milky Way, you're looking at the ecliptic coordinate system plane. And you know what constellations it's visible through. Right now, at this time of year, comes the steam comes out of the teapot and goes right across the top of the sky through Cygnus. So right now, the galactic coordinate system is lined up on this line, like this. If you look at it from above, the origin is towards Sagittarius A star. We live on the blue dot. We point at the black hole in the center, which I have conveniently marked for you with a black hole dot. And then the ecliptic longitude, you just turn to the right with a right-hand bias and measure it in degrees. There's also ecliptic latitude, but since our galaxy is pretty flat, that's not as big a deal, but the longitude is the coordinate everybody uses for most stuff. And we use it to plot out locations within the galaxy relative to where the center is. And then I learned about a new thing that I didn't know before called supergalactic coordinates. And it's really fun when I get to do these things because I don't want to embarrass myself in front of you guys who know a lot of things. So I look up stuff, and every now and then I learn a new thing. After all these years, I learned another new thing. There's such a thing as supergalactic coordinates. They're very obscure, and only cosmologists use these numbers. That's not a thing that you would need for amateur astronomy. Your telescope, even your fancy digital ones, won't know what it is. But it is useful for some people. And what it does is, it turns out, I have learned, that a bunch of local constellation groups that are near us are in approximately a plane. Several of the nearby galaxy clusters are basically flat. I have no idea if that is related to the large sheets and walls of superclusters that exist in the galaxy you might have heard of. It's probably just a local thing. But several of the nearby clusters are approximately in a plane, and they have designated the origin of it is towards the constellation of Cassiopeia at right ascension 2 hours 59 degrees declination. So I've marked that here on this map with a little green marker. That's the origin. It proceeds to the left along the supergalactic latitude, and then perpendicular to that, the supergalactic longitude. And the reference I looked just named a few of the constellations it passes through. I didn't have a precise reference for it, but I'm sure that exists somewhere. But it passes through Pisces, it skims the edge of Andromeda, it goes through the Big Dipper, and it's centered here near constellation Cassiopeia. So that's supergalactic coordinates, and I'm sure somebody out there needs it, but that person is not me. Here's the supergalactic plane, and all these little gray things you cannot read are the names of nearby clusters: the Virgo cluster, the Centaurus cluster, the Sculptor group, the One Galaxy NGC 7482, the Ursa Major group. Those are all nearby small clusters, part of the Virgo supercluster. This is fairly local to us. We're just a chunk of the much larger Virgo supercluster. And in our local neighborhood, this is how the galactic coordinates are aligned with that. Now, the 0 point, as I said, is a specific location in the constellation Cassiopeia. I don't know why they picked it. I'm just reporting the news. Now I'm going to frighten you for a moment. I've done this a long time ago. It's one of those things I had to do in college, and I was thankful I never had to do it again. But to convert equatorial coordinates to altitude azimuth coordinates, you have to do a very large linear math problem with matrices. It's complicated. And I worked through it a few times for homework problems and stuff, and I swore I would not ever do it again if I didn't have to. It uses spherical trigonometry, where the triangles do not, you can have like, in spherical trigonometry, look at this. A right triangle on a sphere can have a right angle at the North Pole, a right angle on the equator, a right angle to go back to the North Pole. It has 3 right angles, and the angles add up to 270 degrees. And in a regular triangle, it's 180. So triangles don't work right on a sphere. You have to learn all these new rules, and everything is like a multiple step trig problem with lots of sines and cosines mixed in. It's really quite complicated, and I remember, just to conclude, this is my last story, I'm almost done. I had to do some conversions. Part of this is taking coordinates in the sky and converting them to altitude and azimuth, and it takes a lot of trig to do it, a lot of spherical trig. So I got taught by this old school astronomer how to navigate like I was a ship captain, and we had to measure the altitude and azimuth of an object with a sextant, and then do a very long, complicated math problem to get right ascension declination, and then somehow it turned into our longitude and latitude on the Earth. And it took a lot of work. So my buddy and I, we went out to a park and took our telescopes. If we're going to do this homework, we're going to also do some observing. So we took our telescopes out, and we're looking at things in the sky, and looking at Saturn, looking at constellations. And I said, I guess we better do the homework. Where's the sextant? And he says, I thought you brought it. So the next night we go out with the sextant, and we're supposed to do it old school, right? So we set out a tub of water, and we're trying to reflect the image off the water like a sailor would. Do it real old school, you know. And it was windy, and the water was like this. So we went out the next night, and we took an artificial horizon mirror, which we carefully leveled, and we did the measurements, and we calculated all the answers, and it put us out in the middle of the ocean, which that's not where we were. So we must have made a measurement error, so we went out again. Each trip's like 40 miles out in the desert. So we go out and do it again, and we did the math again and got the same wrong answer. We go to the professor. We've been out in the desert like 4 times. We can't get this thing to work. How did these ancient sailors do this? This conversion's complicated. This is hard work. And he looks at our paper. He goes, oh yeah, dropped a minus sign right here. And that was the error. So I don't recommend it, but I will tell you this. Who designs those digital telescopes that do altitude and azimuth and tracks the sky for you automatically, this stuff has to be built into it. So the maps are in right ascension declination. And it looks up the right ascension declination and converts it to altitude and azimuth on the fly and calculates into how much do I need to move this telescope to keep the target in there. It's a remarkable thing that they're able to just completely automate that, and you don't have to struggle with it. So there is a need for doing conversions. There are lots of ways to point at things. Most of them depend on the Earth or your face, and they're not universal methods. You got to have an origin somewhere, and we live here, so we get to be the origin most of the other time. I did one time write an article. I published an article in Sky and Telescope once, and it was an article about if you did amateur astronomy on Mars, what would it be like? Of course, the day is a different length, so your clock drives have to be adjusted. The North Pole star is somewhere in Cygnus, so all the coordinate system would have to be adjusted if you're going to do amateur astronomy on Mars. And every planet, therefore, would have to have its own coordinate system. And what a nightmare to convert between one and the other and the next. But if you're ever going to have a telescope on the moon, or you're going to have an observatory on Mars in your colony, you're going to have to learn how to adapt that coordinate system to the ones that we're historically familiar with. Now, the drawing. So I have a big star map to give away. And it is a spare. I swear to you, I've never used it. I've got two more, and I've used one, and I keep one in storage, and I have a spare. So I'm just trying to clear some shelves out, right? Nobody's ever going to use this thing. I hope that one of you finds a use for it. It's a nice conversation piece, even if you're not taking it outside. So I'm going to pull a paper and give away the star map, and I think I'll take questions if you have them, but I'm pretty much done. Here we go. Just shuffling the paper. And our winner is, for the big star map from Will Tyrion's Star Atlas 2000, is Dan. Where's Dan? Dan? V? Okay. We'll try again. John. John Corlett? Where's John? Want it? Hey, clap for him. Now, if you want these, or you want a blank, you can have these back. I just wanted them for the drawing. Anybody have any questions for me before we run out of time?
Is anyone using the center of the universe, or do they have a defined spot for the center of the universe as a coordinate system?
There is no defined center to it.
They can't reverse it back in time to get close?
Well, you have this vision of the Big Bang happening in a place, and then all the stuff rushed out from that place, right?
Mm-hmm.
Back in the 1800s, they thought that place was in the Pleiades. They thought the Pleiades was the center of the universe. But the most advanced version of the Big Bang theory says that when the Big Bang occurred, it not only created the energy that became the stuff, but it created space and time as well. So there was no place. If you use you're probably familiar with the analogy of dots on a balloon expanding, right? So at the beginning, everything was at the center. Every place was at the center as well. So as it expanded, it took all the places with it. That is the correct answer to this question. Where's the center of the universe? The center of the universe is everywhere. It doesn't have a center. The sphere that represents the universe, the surface of a sphere doesn't have a center. The volume has a center, but there are no galaxies there. The surface that represents all the places something can be, the surface of a sphere has no center. So one spot is as good as another spot. My personal preference for the center of the universe is a little town in Utah. It's called Escalante, Utah. It has a post office, a junk store, a couple of houses, and something that used to be a business. I can't tell what it is. And in the junk store, they sell bumper stickers that says, "Welcome to Escalante, center of the universe." It's as good a spot as any, but it doesn't really have a center, so we can't use it as a coordinate.
All right, we have time for just one or two more. All right. Oh, well, okay. Real quick.
I did a WhatsApp about Vera Rubin recently, and she came up with a thesis regarding what I think relates to your supergalactic system. She thought there was a rotation of the galactic cluster about an axis, but it wasn't a popular idea, and she never published.
It's an interesting idea. I would, if I was going to guess, I'd say something like that. But the brief reading that I did, it's just an observational thing. Oh, look, it's a plane. Let's define it. And I didn't see anything that was hypothesizing why it's a plane, really. Yeah. I did get to speak to her one time.
Did you really?
One of my students attended UCLA, and he went to see a talk from her. And so after the speech, he walks up to her and says, "Hi, I learned your name from my high school teacher. I'm going to call him. You want to say hi?" And so I'm like, "Vera Rubin? I'm talking to Vera Rubin?" Thank you. What do you say, you know? Good work. Next time, give me some warning, dude. I come up with a decent question. I babbled for a minute. She laughed and said thank you, and that was it. But I did speak to her. I can at least claim that. Anything else?
All right, thanks everybody for coming.
Thank you. Thank you so much. Take my stuff. Take my stuff. I don't want to take it home.